All right. Can everybody hear me? Okay. So last time we talked about NP-completeness. We're continuing with that discussion. We talked about reductions, reducibilities among problems. And we mentioned a bunch of classical NP-complete problems from a famous paper by Richard Karp back in 1971 or so. And one of them was graph cliques, whether there's a subgraph, a complete subgraph of a certain size. Another was set cover, whether there's some subfamily of subsets that can cover the entire set of some minimal cardinality. Fewer subsets is better. Hamiltonian cycle, whether you can traverse all the edges, rather all the nodes of a graph, and whatever edges you have to traverse to make a complete cycle. Graph colorability, whether you can paint the nodes of a graph in such a way that no two adjacent nodes share the same color, and what's the minimum number of colors necessary to do that. Partition, whether you can take a bunch of numbers, partition them into two subsets that have equal sum. Related to that, the knapsack problem, whether you can maximize the value of a bunch of objects given to some overall weight constraint. Bin packing is how many moving boxes you need at the very least to fit all your stuff in there with the least amount of wasted space or air gaps. And all these problems come in lots of variations and higher dimensions and special cases. Steiner trees how do you interconnect a bunch of points to minimize total wire length. That comes up a lot in circuits and building design and putting fiber optic networks across the country. Lots of different scenarios. All these are NP-complete. Traveling salesman, classical NP-complete problem. How do you traverse a bunch of targets to minimize the total time or distance traversed or fuel spent or whatever the metric is. For graph colorability, we're going to start analyzing it more deeply. So all these problems can be analyzed ad nauseum and with lots of reductions and heuristics and provably good approximation schemes. But let's do it for one problem at least. Dive deeper into it. So we'll do it for graph colorability. So given a graph G and an integer K, is it K colorable? In other words, is there a possible way to paint all the nodes using K separate colors such that no two neighbors in the graph share the same color? And adjacent nodes must have different colors. So here's a graph, and I can say, is it 3 colorable? And for this particular graph, the answer is yeah, because here's a 3 coloring of it. And here's a 3 coloring of this different graph. And here's a 3 coloring of that graph. And but there's a lot of different 3 colorings of a particular graph. Even for this small graph here of 4 nodes, here are all the possible ways of 3 coloring that 4-node graph. And there's about 12 different ways. And that's only for this tiny little graph. For an arbitrary graph, size n, there's exponential number of ways to color it. So you don't want to look at all possibilities to see if this is 3 colorable. You definitely don't want to look at all 12 cases. So we'll get back to graph coloring. But for now, let's look at Karp's original paper. So again, this is 1972, and NP-completeness was being discovered. So that's really the paper that discovered the theory of NP-completeness. That and Cook's paper that proved that SAT is NP-complete. So Cook did the heavy lifting. He showed that everything in NP reduces to SAT, satisfiability. The problem of giving a Boolean formula, whether there's an assignment of the variables that make it true. And then Karp immediately saw the amazing depth and breadth of that paper, and he did the same for 20 other problems, right on the heels of Cook's treatment of satisfiability, showing it's NP-complete. Karp showed that 25 other problems are also NP-complete. They also have that property. So in other words, Karp is saying, so Cook was saying, here's an amazing phenomena. SAT, satisfiability, is the hardest problem in NP, and nothing is harder than that. If you can solve that problem with an efficient algorithm, all of NP all of a sudden is solvable with an efficient algorithm through SAT, through the reduction. And that's amazing enough. And then Karp, the very next year, published a paper saying, yeah, that is amazing. And not only that, dozens and dozens of other problems have the exact same property. So there's nothing special about SAT. with respect to that property. It's just historically the very first problem that was proven to be NP-complete. And then Karp did that for a whole bunch of others. And he, of course, gives credit to Cook. So, Karp, in his very second page, says, this paper was stimulated by the work of Stephen Cook, 1971, the previous year, and rests on an important theorem which appears in his paper. And that's the theorem that we saw a couple of lectures ago, reducing all of NP to satisfiability. And he knows exactly what he's doing, what he's saying. It's not an accident or oblique. He says, we show that a large number of classic unsolved problems of covering, matching, packing, routing, assignment, sequencing, blah, 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 in a sense that each of them possesses a polynomial bounded algorithm or none of them does. So he's grouping them together into one big equivalence class. That's NP, or NP-complete problems, that class. And then he defines the class P, which of course is all problems which are solvable in polynomial time, deterministic polynomial time. NP is non-deterministic polynomial time. And he goes through and makes some definitions. And he talks about problems that are in P and problems that are in NP. Talks about what a deterministic algorithm is. Basically, it's something that only has a single next state from every state that it's in. It's a deterministic, unique choice of where to go next in the algorithm, in the execution. You can go several different places like you can for non-deterministic algorithms. And then he talks about Cook's theorem and talks about satisfiability. And he also mentions the satisfiability where you have at most 2 literals per clause. That's 2 sat. That is solvable in polynomial time. And for extra credit, I asked you to solve it in polynomial time. Show me how it's done. So other highlights of his paper, he talks about non-deterministic Turing machines, and then satisfiability in general. He says Cook showed that if a problem is an NP, then it reduces the satisfiability. That's the reduction symbol here. That's polynomial time reduces the satisfiability. We showed it on a slide as A and B and F, and polynomial time transformation of A to B, and that's what this refers to. This symbol here, that symbol there is the transformation, polynomial time reducibility, or polynomial time transformation of one problem to another problem. And then he gives a huge laundry list. He calls them the complete problems. The term NP-complete was made up a little later, but he just called them complete. So now we call them NP-complete. Just like Turing, when he invented his amazing machines, the model of computation that we all know and love and study, and is still studied today, he didn't call those machines Turing machines. He didn't call them my machines because he was Turing. He just called them machines, and then now we call them Turing machines. So here we call it NP-complete problems. But he gives a long laundry list. But this page right here is where NP-complete theory, NP-completeness theory started, amazingly enough. And here's this long list of problems. Satisfiability, we already know what that is. Clique problem, we know what that is. Set cover, we discussed that. Right? Hamiltonian cycles, we talked about that. And there's a bunch of others too, 0-1 integer programming, and the list goes on and on. Satisfiability with at most 3 literals per clause. That's 3 sat here, which we already talked about. 3 sat, 3 literals, at most 3 variables with their negations per each clause of the formula. He mentions that too. Chromatic number, that's coloring. So that's graph coloring, we already discussed that. And we will discuss it a lot more. Cliques, we talked about Steiner trees, that's right here. Knapsack, when you run out of burning house, you can only carry so much. You want to maximize the value that you can carry. It's the same problem with looters. When you have a civil riot and looters kind of break into a storefront and want to grab stuff and run away from the police. They're solving the knapsack problem, or at least a version of it. Right? They want to run away with as much as they can carry, but that has the greatest value, not just by weight, but by value, given the weight constraint. Max cut, partition. Okay, so we already mentioned a bunch of these, maybe half of these problems here on this list. And then he says that satisfiability reduces the clique, and he gives the reduction. And more generally, he gives reductions for all of these problems. He shows that they're all NP complete. So remember, Cook already showed that all of NP reduces to SAT. And Karp shows that, for example, SAT reduces to clique. And so if you could show that everything in NP reduces to SAT, and separately that all of that SAT reduces to clique, then combining these two results and composing the two transformations, that shows that all of NP reduces to clique through SAT by composing these two transformations. How many get that? It's like calling a subroutine. Except this is a subroutine in math is a lemma or even a theorem. Right? Theorems can cite other theorems as part of their own proofs. And so in math, a subroutine is a lemma. Right? So if you can combine these two transformations, you get another transformation end to end, and you keep going. And now that you know that clique is NP complete, you can reduce that to node cover. And so all of NP reduces to satisfiability, which reduces to clique, which reduces to node cover. So now all of NP reduces to node cover. And all these transformations are polynomial time transformations, because that little f between A and B and that abstract slide picture, that f has to be polynomial time. The nice thing about polynomials, there's a lot of nice things about them, and one of the nice things about polynomials is that if you take a polynomial f and a polynomial g, and compose them by coming up with f of g of x, that too is a polynomial. The composition of two polynomials is a polynomial. How many understand that and believe that? Yeah. There's only 5 hands rising, so let me repeat. You have a polynomial, say third degree polynomial f. Let's say we have a fourth degree polynomial g. And so it's f of x is a polynomial, g of x is a polynomial. If I say f of g of x, compose the two polynomials, that too is a polynomial. How many believe that? Good, that's one more hand. What's the degree of f of g of x? If f is 3 and degree 3 and g is degree 4, the degree of f of g, it's degree, I hear 7. That's not right. Say 7. 12. Oh, okay. 12 outnumber. Anybody want to argue why it's 12 and not 7? So I have, f of x is x cubed. G of x is x to the 4th. F of g of x is what? X to the 4th to the 3rd, which is x to the 12, not 7. I mean, it's easy to get confused about, but look, either way, 7 or 12, they're both polynomials, which is the main point of what I'm trying to say. Okay, polynomials composed to give other polynomials. So this diagram here, it's not a data structure. It's not just a tree. It's a schema of the proofs in the rest of the paper of which was transformed to what. The problem was transformed to which other problem. So each edge here in this tree is a proof, is a transformation of a problem to another problem through some f in this A to B abstract diagram that we saw several times now. How many understand that? Each edge is a proof here, a mathematical proof. And I only see 5 hands rising. So let me repeat that, because this is important. If you don't understand what this diagram means, nothing else will make sense to you. Okay. Each node in this diagram, in this tree, this node and that node, that's a problem. It's an entire infinite set of instances of a problem, a combinatorial problem, right? So satisfiability, that's the set of all satisfiable Boolean formula. Boolean formula for which there exists an assignment of the variables that makes it true. That's what satisfiability is. So that node up here at the root of the tree is an entire problem, which is an infinite set of instances of the problem. In the case of satisfiability, it's a set of all satisfiable Boolean formula. Because some Boolean formulas are satisfiable, others are not. Okay. Each one of these other nodes is exactly the same type of object. It's a problem. It's an infinite set of instances of that problem. So, for example, clique is the problem of, I give you a graph and you tell me if there's a subgraph, a complete subgraph of size k. So I give you a graph and I give you an integer k, and I say, does this graph that I'm giving you has a clique of size 7, say, where k is 7. A clique is a complete subgraph. Complete subgraph means everything is connected to everything else within the clique. Everybody's a friend of everybody else. Complete social network there, to use colloquial terms. Okay? And satisfiability can be reduced in polynomial time to the problem of clique, determining cliques. We'll actually show the transformation. We're about to show the transformation. In fact, we'll show several of these transformations. We're not going to show all 20 or so transformations. That'll be kind of overkill and a waste of time. But once you see 2 or 3 of them, you get the idea of how it goes. And some of them are more complicated than others. Right. We're going to show this transformation here, in particular, satisfy 3-sat to graph coloring. Chromatic number means graph coloring. It's just a different name. This transformation here will take us probably a good half hour to go through. And some of these other ones are probably even more. But we're not going to go through all of them, probably much to your relief. But I want you to see at least several so you can see the idea of how it works. Okay. How all these problems are related to one another. So each node here is a problem. Each edge here is a reduction of a problem to another problem. The 2 problems that hang off the tips of that edge. So this here is a mathematical proof schema. In particular, it's the one that Karp used in his 1972 paper to show that all of these problems are NP-complete. Cook showed the first one. And the first is always the hardest because you have nothing to work off of. You got to show that all of NP reduces to satisfiability. But once you do that, all you got to show is that satisfiability reduces to a single other problem, clique, to show that clique is NP-complete. You don't have to show that all of NP reduces to clique because you're composing 2 transformations. All of NP to SAT, which is this one, and then SAT to clique, and then the composition of them shows that all of NP reduces to clique. So Cook had to do it the hard way. He had to do the heavy lifting of showing that an arbitrary Turing machine computation that runs in non-deterministic polynomial time can be always reduced to a satisfiability instance, to a Boolean formula that's satisfiable if and only if that computation ends up with success, that it runs to completion with the answer yes. So once that's done, you can use NP-complete problems to show other NP-complete problems are NP-complete via a bunch of compositions of other transformations. And these other transformations could be much easier than Cook's, and sometimes they're much, much more difficult. Some people have gotten PhDs to show that a single pair of problems reduce to one another in polynomial time, or in particular one reduces to the other, not necessarily the other way around even. And that proof was 100 pages long, literally. It's an entire PhD dissertation. And they worked on it for years because it wasn't easy to do. Okay, so you'll see a few ones that are trivial and 1 or 2 or 3 that are not so trivial. And I'm just telling you there are ones that are much, much harder than those even. Okay, how many understand what this picture shows now a little better? Good, a lot more people, that's good. Any questions about this? Yeah.
So I'm wondering, since you said who proved all the NP problems were reducible to satisfiability problems, what if there comes a problem in the future which might not be able to reduce into the satisfiability problem?
Well, he showed it for all of NP. So he showed it for all infinite number of problems that are in NP. He showed it in general. So there is no problem. Once he showed it, there is no problem in NP that doesn't reduce the satisfiability because he showed that all of them do. How did he do it? Well, we've shown some slides on it. That was kind of the sketch of the proof, not all the gory details. If you really want to know all the gory details, there's a good chapter in the book that goes through some of that, and there's lots of other books I put on the website and on the Colab site that give you half a dozen different explanations of how Cook's theorem works. And there's a wiki page that does the same and so on. I urge you to look at some of that stuff. I urge you to look at the wiki page of Cook's theorem and how everything in NP reduces to satisfiability and so on, because it's hard to wrap your mind around it. I mean, it's a monumental achievement. He showed that there's an infinite number of problems that all reduce to SAT. And he didn't take an infinite amount of time to do that, obviously. He did it in a 10-page paper after thinking about it for a couple of years. So that's one of the beauties of NP-completeness theory. It allows you to treat entire infinite classes of problems as if they were bunched together and you apply the result to all of them simultaneously. I mean, incredible economy of scale in terms of mathematical analysis and their ability to analyze problems and dissect and their properties and make concrete mathematical statements about them. It's great when you can handle an infinite class of objects simultaneously with the same treatment, as opposed to doing them one at a time. Because that before NP-completeness came around, people were doing it one at a time, painfully, and with difficulty, and they couldn't come up with polynomial time algorithms for any of these problems that they try to solve separately. I mean, people literally in companies and in government and in industry and in academia said, okay, this year I'm going to make it my project to show that the problem of node cover is solvable in polynomial time by trying to find an algorithm for it. So, and they tried and they couldn't. Okay, so they said, okay, next year we'll try handling traveling salesmen to see if we can come up with a polynomial time algorithm for traveling salesmen. And another group said, okay, well, you're working on traveling salesmen. We're going to try to come up with a polynomial time algorithm for Hamiltonian cycles or Steiner trees or whatever. And they all worked and failed. None of them succeeded in finding polynomial time for algorithms for any of these problems. And they kept switching around, trying different problems. And AT&T has been trying for decades to solve some of these problems. They put millions of dollars and thousands of person hours for each problem trying to solve them in polynomial time with an exact solution. And they couldn't, and they didn't understand why. So they moved to another. But they didn't realize that they're all related. They're all tied together. If you can solve one of them in polynomial time, all of them instantly will collapse into polynomial time simply by the transformations. So they didn't have this notion that they're all bunched together with this amazing relationship called NP-completeness. They thought they were just isolated problems that have nothing to do with each other. Right? How many understand all this kind of good? So it's an incredible human achievement that we're looking at here. It saves us so much work. Because next time, a problem is NP-complete, you're not going to bother to try solving it exactly. You won't. You'll save all that time and money and energy and potential embarrassment for looking kind of silly and stupid for not being able to do it. You'll say, the reason I can't do it, I know exactly why I can't do it and why I shouldn't even try to do it is because it's one of those problems. And, thousands of very, very smart people for decades and spending millions of hours and probably billions of dollars by now tried to solve these problems separately, not knowing they're related like this, and they all failed. And for the same reason, I will probably fail too, because it's just one more of those problems. So instead, what I'm going to do is be more productive and more useful with my time and money and my company's resources and say, okay, I know for sure I shouldn't try to solve it exactly, so I'm going to try to come up with a heuristic, an approximation algorithm that gives me an okay solution, not necessarily the best possible, which will be the exact solution, because we know that's not likely to happen. And I'll try to come up with an approximation algorithm, a heuristic, and that'll be good enough, and that the company can move on and monetize that instead. And that's a tremendous shortcut, very effective, very practical. Literally, it's worth its weight in gold. This kind of insight. Okay, so that's the schema he used, and that's a picture from his paper, actually. And here he shows how to reduce satisfiability to 3-sat. And he does exactly what we did earlier. Remember, we took a large, every large clause that's bigger than 3 and reduced it to a bunch of little clauses that are 3 each and connected them with a few dummy variables that we invented such that the big clause is satisfiable if all these little clauses are satisfiable too, and there's only 3 in each, 3 literals in each. How many remember that? Good. So that's where this is in the paper. He says replace a clause, blah, 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 a big clause, with a bunch of little clauses. And that's how that reduction goes. So that reduction is relatively straightforward. We've already seen it. Reducing satisfiability to 3-sat. So this we've already seen the proof for. Later today, not too long from now, we'll see this proof here. And that's a much harder proof. And we might see a few other simpler, shorter proofs of other reductions in between. Okay, so that's where he shows 3-sat is NP-complete from reduction from sat. And here he talks about reduction of satisfiability to clique. And there's problems here that are p-space complete. The notion of completeness is not just for NP and P. every complexity class has completeness associated with it. It's a very ubiquitous phenomena. It's a very sweeping phenomena. So we talk about NP-completeness, we talk about completeness with respect to the class NP. And there's also P-completeness, completeness with respect to the class P. And linear programming is P-complete, turns out. But there's also other complexity classes. There's lots and lots of complexity classes. Polynomial space is another complexity class. Whether polynomial space is equal to NP or to P, we don't know. It's an open question. But there are P-space complete problems. It contains all of P, contains all of NP, and could potentially contain more things. It could be a much broader class. And there are problems which are P-space complete. And one of them is equivalence of regular expressions. Another is an equivalence of a pair of non-deterministic finite automata. So if I give you two regular expressions, the question of whether they're equivalent to one another, whether they denote the same set of strings, that's P-space complete, which is even worse than NP-complete. Okay. Don't want to be presumptuous. How many know what a regular expression is? Oh, good. So most of you. So if I give you two regular expressions, that's a very tough problem to determine whether they're equivalent to one another. Nobody knows a polynomial time algorithm to do this deterministically. In fact, nobody even knows a non-deterministic polynomial time to do it. But we know polynomial space algorithms to do it that run in exponential time. Okay, so that problem is even harder than SAT. Same thing for the equivalence of two finite automata. So some problems are open to this day. So it talks about problems in NP which are not known to be complete. So graph isomorphism, whether two graphs are isomorphic to one another, whether you can map the nodes of one graph onto the nodes of the other graph that preserve all the edges. That's what graph isomorphism is. It means the two graphs are the same modulo a relabeling of the nodes. How many understand that, graph isomorphism? That problem is very hard, but it's not known to be as hard as being NP complete. So it's somewhere in between P and NP complete. We don't know which yet. And remember, all of P is going to be equal to NP, in which case everything in NP is NP complete, and everything in P is NP complete too. The problem of primality, I give you a number, you tell me if it's prime or not. Right? Even the Greeks were wondering about that, like the sieve of Aristophanes and lots of ancient algorithms to test primality. But nobody knew of a polynomial time algorithm for primality until 2004, a deterministic polynomial time for primality. And that was a big deal. People have been trying to solve that for literally 2,000 plus years, since Greek times. How do you quickly determine if a number is prime or not? But back in '72, when this paper was written, he didn't know, nobody knew, whether primality testing is in P. Fast forward 30 years, 30 plus years, and now we know it's in P. So primality is not as hard necessarily as NP complete type problems, unless P is equal to NP, in which case everything is NP complete, trivially. And by the way, a polynomial time deterministic algorithm for primality testing was invented by some professor from India and several of his undergraduate students. That was it. How many heard of that result? Yeah, it was amazing. You know, people literally for over 2,000 years tried to come up with good algorithms, and then a few undergraduates and their professor found one. So never underestimate the power of undergraduates working with some professor, or even by themselves. Okay, so problem transformations. Let's talk a little bit about that some more. To solve a problem, we efficiently transform it to another problem, and then use a solver for the other problem to solve the first problem through this transformation. So we already mentioned that satisfiability could be reduced to graph colorability. And by the way, these little Turing machine kind of icons, I use them to denote a transformation. So it's some machine that crunches out the transformation of one problem to another problem. So you reduce or transform satisfiability to colorability, and then you feed the colorability instance to some solver for colorability, and it solves the colorability instance, and from that you derive back the satisfying assignment. That's kind of the schema, and we're going to go through showing you these transformations much more explicitly, and it's going to be non-trivial. But first, let's go back to the issue of decision versus optimization. So if you have a decision problem, it's a yes-no question. It's a Boolean query. So it's a set membership, like in the A and in the B, in this abstract diagram that we keep alluding to and seeing over and over again. So given the Boolean formula, is it satisfiable? So I give you a Boolean formula here. You know, this is and, so I'm kind of scrunching it so it fits in the margin. Here's a Boolean formula asking you, is it satisfiable, yes or no? Now, I'm not asking you for the satisfying assignment if it's satisfiable. I'm just wanting you to tell me that there is an assignment, and of course, you need to be correct. You can't lie. And if there is an assignment, you say yes, and I'm happy. I know it's satisfiable. I don't know necessarily how it's satisfied, the actual assignment that satisfies. There could be many assignments that satisfy. Don't get me wrong. It's not unique, right? If it exists. But that's a yes-no question, okay? A decision problem. Given a graph, is it three-colorable? So I give you a graph like this, and you say, is it three-colorable or not? You're not necessarily giving me the coloring of the graph, the three coloring of the graph. You just tell me that one exists. You assure me it exists, and I say, good. Thanks for telling me. Now I know. But I still don't have the actual three coloring that, you know, makes that true. I just know that one such coloring exists. Okay, so that's another example of a decision problem. Given a graph in a parameter k, does it contain a k-clique? So I say, does this graph contain a 5-clique? And yeah, it does, but you don't necessarily give it a 5-clique. So these are examples of decision problems, yes, no, Boolean queries. But the optimization problem asks for something more. It asks not only for you to tell me that this assignment that this Boolean formula is satisfiable, but it asks, what is a satisfying assignment? Show me the assignment that satisfies. Give it to me. The x's and the y's and the z's. Given a graph, show me the three coloring. Like show me that there's the k-clique. Not just tell me that one exists. And still you'd be right, but I want to see it. So I want to see the answer, not just know that an answer exists. Right? Show me the three coloring, show me the k-clique, and so on. Now here's a perhaps surprising theorem, but it's not that surprising because we talked about this before, and you'll see in a minute the context. Solving a decision problem is not harder than solving its optimization version. You know, determining that a Boolean assignment exists that satisfies the formula is not hard. Is as hard as actually giving the assignment. Well, let's put it that way. Giving the assignment is not any harder than actually determining that one exists. How can that be? How can giving the assignment or giving the clique or showing the Hamiltonian cycle or finding a coloring, the actual coloring, could be no harder than actually just knowing that one exists and being correct about it, of course. How can it be? Because when I give you a 5-clique, for sure it exists. Otherwise I couldn't give it to you. And if I give it to you, you can easily check if it's a 5-clique or not, so you can catch me if I'm lying. But if I just say, yeah, there's a 5-clique, trust me, take my word for it, don't worry about it, there's a 5-clique there. Well, I may be right, but that doesn't seem to give you much information about where's the 5-clique, right? How many see the difference between these two scenarios? Yeah, one is a very provable scenario, a situation where I give you the answer and you can check. The other one, I just tell you an answer exists, and of course I'm always correct. I'm never lying, but it doesn't seem to give you much information beyond the yes/no bit that a solution exists. So how can they be equivalent? Well, we're about to see how, when we already kind of saw how before, but I'll remind you. So what we're saying is that, so obviously, if I solve the optimization version, I'm also solving the existence. If I give you the clique, certainly it must exist, otherwise I couldn't give it to you. If I give you the assignment that satisfies, obviously it exists, because otherwise I couldn't give you the satisfying assignment, and then you can check that it's actually satisfying. But how is it the other way around? Well, here is how it is. So we're going to show that a decision problem is in P if and only if its optimization version is in P. They're tied together. These decision versions and optimization versions, they're tied together. And once we prove this, all we're going to need to talk about from now going forward is just decision versions. Because it'll be obvious how to convert a decision version to the optimization version equivalent. Okay? So you can basically build an optimizer from a decider. So let's say you have a decider for satisfiability. You give a Boolean formula and it says yes or no. It's satisfiable or it's not. What is the Boolean formula that you feed it? So I'm going to treat this as a black box. So it's a yes/no decider for Boolean formulas which are satisfiable. But it doesn't give you the satisfying assignment. It just says yes, it's satisfiable, or no, it isn't. But let's say you want to know the satisfying assignment, the actual assignment of the variables that satisfies this formula, not just to know that it's satisfiable and walk away in victory, not knowing what an actual satisfying assignment is. You want to know the assignment that satisfies. So let's go through this exercise. So you're going to ask it whether it's satisfiable or not. And you can ask it, separate questions. So for example, let's say the formula is called P. So P is equal to this big Boolean formula here. It could be a very large formula. I'm just showing a small example. But you're going to ask the decider, is P and X satisfiable? P is the formula, X is just one variable, and the AND is just the conjunction that we know and love from Boolean logic, the AND operator. So if I ask it, is P and X satisfiable, and it says yes, or it says no, we could also ask it about P and X not, if it's satisfiable or not. Then you can say yes or no. Okay. So let's say P and X, it says, is satisfiable. What do you know about X and P? And by the way, these subroutines, these deciders, they never lie. So we don't have to worry about malicious decider that lies to you and tries to fool you. No, algorithms always give you the correct answer. So this decider always correct. When it says yes, it's satisfiable. When it says no, it's not satisfiable. There's no two ways around it. Okay. So if this decider tells you that this formula, P and X, is satisfiable, what can you tell me about X and P with respect to satisfiability? That tells you something. So if I say P and X is satisfiable, and separately it says that P is satisfiable also. You call it twice. Once with P and one with P and X. So what does that tell you about X with respect to satisfiability and P? It tells you that there is a satisfying assignment for P in which X is equal to 1, where X is true. How many understand that? Because if it says P is satisfiable, well, there is a satisfying assignment for P. If it says that P and X is also satisfiable, that means there's a satisfying assignment for P where X is also 1, not 0. There could also be a separate one where X is 0. How many understand that? One doesn't exclude the other. But at least there's one where X is equal to 1. So what are you going to do next? So you just squeezed one bit of information about the satisfying assignment by calling it twice. What are you going to do next? Well, before we even ask that, let's see if it says no. If it says P and X is not satisfiable, so let's say P is satisfiable, but P and X is not satisfiable. What does that tell you about X in a satisfying assignment for P? Not a tough question. It's got to be false. But there's still got to be a satisfying assignment because P was satisfiable. And X has to be either 0 or 1. So if P and X was not satisfiable, P and X not better be satisfiable. How many get that? Yeah. And you can ask her that question too. But X is true if P and X not is not satisfiable, or if P and X is satisfiable. Both of these situations lead to the conclusion that X must be true in some satisfying assignment. What if it says no here? P and X is not satisfiable, and P and not X is satisfiable. What is this alternative situation here in red? See if you're... X must be false in some satisfying assignment. How many understand it so far? Okay, pretty straightforward, right? And of course, there's other cases. What if it says P and X is not satisfiable and P and X not? That's not satisfiable either. That'll be weird, but I mean, what if you get these two answers back as no and no from the decider? What does that tell you? What's it's wrong? What do you mean by wrong? It can't be correct. P can't be satisfiable if both P and X is not satisfiable and P and X not is also not satisfiable. That's a logical contradiction. How many understand that? Yeah, you can't have it both ways. And still P be satisfied. If P is not satisfiable, sure you can have it. But if P is satisfiable, you can't have these two situations both be false at the same time. So if you get a no here and a no here, P can't be satisfiable. That's your conclusion there. And of course, there's one more case where you get yes here and yes here. If P and X is satisfiable and P and X not is also satisfiable, that could happen. What does that tell you about X? Hardware people have a name for that. It's a don't care. How many see that? Yeah. Doesn't matter what X is. It works either way. Okay. For the formula to be satisfiable, with or without X being true or false or either one. So it's a don't care situation, which is nice. It gives you more degrees of freedom to design your hardware or make your conclusions or whatever. Gives you more flexibility. Okay. So now by now we extracted from the decider the value of X in some satisfying assignment. What do you do next? Do it again for another variable and another variable, and keep squeezing it for information one bit at a time. In other words, you iterate. And you iterate with more and more variables, one variable at a time. So now that you get your answer, you know what X should be, then plug something in for the X, or just keep it out here, whether it's the X or the X prime, and then say and Y, and Z, and W. Keep adding variables one at a time. Keep running it through the decider. At each iteration, you'll squeeze one more bit out of it. And that's how you do it. So in real life, when do you run into this situation? So so a decider just gives you yes, no answers. But here we squeezed the actual solution out of it, not the yes, no, the actual long solution, all the assignments of all the variables that make it happen. The satisfiability happen here for this formula. So you're playing this game with a decider by calling it over and over and over again. What game are you playing with it? Hint, hint. We actually played this game in class 2 lectures ago. How many remember that? What was the name of the game? "21 questions." So you're playing 21 questions with a decider, and at the end you know it's a zebra. How many remember that discussion? Good. That's exactly what's happening here. And what's this 21? Why is it 21? Why is it not 51 questions or 1,000 questions or just 3 questions? What's the 21 referring to, sort of, asymptotically? It's the log of the solution space. It's a log of a number of species of animals, minerals, and vegetables that you're trying to narrow down to a zebra or a diamond or whatever the situation is. And then, 2 to the 21 is about, 2 million. Yeah, so, there's 2 million objects somebody can think of. Actually, probably a lot less, and you'd be hard-pressed for thinking about 2 million separate objects. But that's enough. So 21 questions should be enough. It covers a solution space of about 2 million objects. In particular, it's the log of the size of the space. Okay? So if you have to call a subroutine and runs in polynomial time, a logarithmic number of times in the size, the number of bits in the answer, that's not too onerous, right? That will still keep you in polynomial time. So the point is that any decider could be turned into an optimizer. Again, decider says yes, no. Optimizer gives you the answer, the full, long answer of the satisfying assignment, or the colorability, or the Hamiltonian cycle, or the big Steiner tree that spans everything, or whatever else you're looking for. Whereas the decider just tells you that one exists. Okay. So this is a very general scheme. It works across all problems and all situations. So that means what? Without loss of generality now, we can just talk about deciders, not optimizers, and analyze the complexity of them and how they relate and how they transform to one another. How many understand the schema here, the logical, mathematical schema So we've just simplified our lives a whole lot with this observation. We're playing 21 questions. Okay. We're going to squeeze the decider one bit at a time until it gives us the answer. So we might as well just, from now on, not even deal with things that gives us answers. Just decide for us. Because we know we can always squeeze them if we need to, like this, by playing 21 questions with them. So that really simplifies things. Okay. So, graph cliques. So the clique problem is I give you a graph and some parameter k, integer, and ask you, is there a subgraph of size k? Is there a complete graph of size k? A k clique. So it's NP-complete. We're about to prove it. I'm going to show you a transformation. So we're going to reduce it from 3 sat. Because remember, everything already reduced, everything in NP reduced to 3 sat, through sat. Right? So now we reduce 3 sat to clique, and then that will make clique NP-complete. Because everything now in NP would be reducible to clique through this new transformation that we're about to see in the next 2 minutes on this very slide. So the literals become nodes, the clauses induce groups, and then you connect all the intergroup nodes that are compatible with one another through the corresponding clauses. Well, what does that mean? Let's look at an example. Let's say we have this Boolean formula here, and we're going to turn this Boolean formula into a graph clique instance, such that this Boolean formula is satisfiable if and only if that graph that we'll come up with has a clique in it, has a 3 clique in it. So here are all the nodes from all the clauses. I'm going to color code them. So the first clause gives you this x, y, and z nodes here in this new graph that I'm transforming this formula into. These 3 green variables and negations of variables in this second clause give you these 3 nodes here, x naught, y naught, and z. This blue clause gives you these 3 blue nodes here. And I'm going to connect nodes to other nodes that are compatible, compatible with it, consistent with it. So this x here, if this x is true, this y naught could still be true, and there's no contradiction. In other words, in some satisfying assignment, this x could be true, and this y naught could also be true. But this x cannot be true in this clause, and this x naught also true in that clause because they're oppositely related. X and x naught cannot both be true. So there is no edge between this x and this x naught. But there's nothing logically preventing this x to be true and this z to be true too, because they're independent clauses and they're not related. How many understand that? So certain edges are there, certain edges are not there. Okay? And I'm going to complete all the other edges there. The y of this could be compatible with a z in that clause. The y can also be compatible with the x naught in this clause, but it cannot be compatible with the y naught in this clause, so there's no edge between the y and the y naught. Okay, and I keep going like this, and I create all the edges that are compatible with between nodes that are compatible with other nodes with respect to satisfiability in this formula, and I come up with this big messy graph. And then I look for a 3 clique here. Notice that no red node is connected to any other red node. No green node is connected to any other green nodes. It's only compatibility across clauses, as you want it to be. Right? So now if you find a clique in this graph, let's say I look at this 3 clique, and there's many other 3 cliques, by the way. It's not the unique solution. But this particular 3 clique, where the x connects to the y naught connects to the z naught, this 3 clique that I highlight in purple, 3 nodes all connected to one another, it's a triangle. It's also a 3 clique. What does that tell you, this 3 clique? That if x was true, y naught could be true, and z naught could be true. Right? In other words, y is false and z is false. That means for the complements to be true. And that assignment satisfies this formula here. Let's check. If x is true, that makes the first clause true. Okay. If y is false, that makes the second clause true, because there's a y naught here. If z is false, then z naught is true, and this whole blue becomes true. And they're all compatible with one another. None of them contradict any of the others in this logical kind of negating way. And that assignment becomes a satisfying assignment for this formula because that purple thing is a clique. How many see how the two problems are related now? Yeah. So solving cliques is solving satisfiability in disguise via this transformation. This transformation is very, very important. It's what makes a clique solver into a SAT solver. So even if a SAT solver, we don't know how to solve SAT, but let's say we knew how to solve clique. You can take the SAT, convert it to a clique, solve the clique, and you'd have the solution for a SAT. Okay. And now you see how it works. If there was a efficient polynomial time algorithm for clique, we can exploit it into an efficient polynomial time algorithm for SAT via this trick. The clique solver wouldn't even know they're solving SAT, because all they're doing is solving cliques in graphs. Graphs are very different than Boolean formulas, but not really. Graphs are Boolean formulas in disguise in this sense, with respect to satisfiability. How many get this? It's subtle, and it's beautiful, and it's general, and this phenomenon happens over and over and over again. You'll see that all these problems are all interrelated. They're all each other in disguise. All of NP, all the NP-complete problems in particular, are all interrelated in this fashion. If you can solve one efficiently, you can exploit the solver for it to solve all of the others efficiently too. And that's the beauty of NP-completeness. That's how it goes. Question?
So this graph can have like multiple cliques. Then we have to check for every clique.
He's saying this graph has multiple cliques. Do we have to check all the other cliques? Very good question. What do you guys say to that? How many say you have to check all the cliques? How many say you found one clique, you're done? Yeah. Why? It's true. You find one clique, you're done. That's it. That'll get you a satisfying assignment.
But to find one, don't we have to check like every other clique?
So first of all, let's just say the answer to finding a clique is not unique. There can be many cliques of size k. Just like there's many satisfying assignments for a Boolean formula. The answer is almost never unique. There could be lots and lots of different ways to satisfy a Boolean formula. But now he's asking an even more subtle question. So there could be many, many solutions, but all you got to do is find one. When you have to find a satisfying formula, a satisfying assignment for the formula, it doesn't ever say you have to find all of them. Actually, there are problems where you have to find all of them. They're called P-sharp, sharp P-complete, but let's not even go into that swamp. It's much more complicated than this. But if you find one solution, you're done. Find one clique, you're done. You find one satisfying assignment, you're done. You don't have to find all the others, or even worry about whether there are any others, more generally. Now he's asking a more subtle question, saying, how do we find this clique efficiently without looking at all possibilities? Very good question. What do you say to that? It's a subtle question, because the answer is a little oblique. How do you find that clique without looking at all possibilities? And there's an exponential number of different, groups of nodes that form cliques, potentially, that you may have to check. How do you find that clique efficiently? The answer is what? How do you find cliques efficiently? We can't, or we don't know how. We have no idea how to find cliques efficiently. But if we did know how to find cliques efficiently, we'd immediately be able to find satisfying assignments efficiently as well. That's the point, that they're tied together. Even though we don't know the answers to either one, an answer to one will immediately give you an answer to the other in terms of efficient algorithms. That's exactly the point of NP-completeness. Together they stand or together they fall. How do you solve any one of them? We have no idea. But what we do know is that if you solve any one of them, all of them will collapse immediately into efficient solutions via these transformations. How many get that? Good. That's exactly what we're trying to show here. It's an if. It's an if-then. If we can find an efficient algorithm for clique, then we immediately have an efficient algorithm for SAT through this trickery here, through this transformation. Excellent question. Any other questions so far? Because we're going to go through a bunch of these transformations. Some of them will not be easy. This one was an easy one. So what have we done here? We reduced SAT to clique in such a way that if you have an efficient clique solver, immediately that gives you an efficient SAT solver from it. In other words, we converted a clique solver into a SAT solver. That means that clique is NP-complete. Because we already know that all of NP reduces to SAT. All of SAT, that was Cook's there. Right? SAT reduces to 3-SAT. That was one of Karp's results. Now we're showing that 3-SAT reduces to clique. compose these three transformations means all of NP reduces to clique. Clique is NP complete. Of course, we also have to show that clique is an NP. Remember, NP complete there's two conditions for something to be NP complete. First, it has to be NP hard. It means all of NP has to reduce to it. Two, it itself must be an NP. That's the easy part, usually. How do you prove that SAT is an NP? How do you prove that clique is an NP? Easy. Come up with a non-deterministic polynomial algorithm for SAT. How do you do that? Start at the top, say x is 1, x is 0. Branch. Given that x, branch on y being 0 or 1. Now you have 4 branches. Then branch on z being 0 or 1. Now you have 8 branches. After n branch points, you'll have an exponential number of threads, but the height of the tree, which is the complexity of the non-deterministic algorithm, is only linear, the number of variables, because you branch at each point on a variable. And at the end, what do? After you make all these series of guesses, you have to do something else that's important. It's easy to do, but it's important to do it. Check. How many get that? You have to check that sequence of yeses and nos for the x's and the y's and the z's actually works. And if it works, and it's easy to show that it works. You just plug it in, make sure that you get a true out of the old formula, given that assignment of the x's and the y's and the z's. If it works, you raise your hands in victory. You're done, and you're done in non-deterministic linear time. Doing it deterministically, we don't know how to do it efficiently. We know how to do it non-efficiently in deterministic time. Try all combinations, but there's an exponential number of combinations to do deterministically. But non-deterministically is easy. So it's definitely an NP. We just showed a linear time non-deterministic algorithm for SAT. What's a linear time non-deterministic algorithm for clique? Very similar to what we just showed. The structure is almost identical. How do you solve clique in non-deterministic polynomial time? Take a node, decide if it's in or out of your clique. Branch on that, non-deterministically. Then pick another node, decide if it's in or out of your clique, and so on and so on. After n levels, you would have picked every single subset. Then what do you do at the bottom? One word. Do you want to buy a vowel? Begins with a C. Check. Yeah. Why check? Because your guesses may have been wrong. You have to find the one that works. Right? So you check. Once you check, you can declare victory if it is a clique. Because all you got to do is go there. Check every node is connected to every other node in this clique that you guessed all the way down. And that's a non-deterministic algorithm that finds cliques. Non-deterministic algorithm that finds cliques, not a deterministic one. Deterministically, we don't know how to do it efficiently. We know how to do it not efficiently. How do you not efficiently find cliques deterministically? In one sentence. Or even in 2 words. Brute force, yeah. If you can say it in 2 words, don't use a 3rd and a 4th and a 10th word. Brute force. What does brute force mean? Look at all possibilities. Just enumerate all possible scenarios. Well, that's an exponential number of them. That's the problem. If you want to do it deterministically. Non-deterministically, you can do it in linear time. That's the beauty of the non-determinism. It's very efficient. The question is, how efficient is it? Well, we don't know. We don't know if you can reduce exponential time to polynomial time in the worst case. That's P is equal to NP question, right? Okay, so we converted a SAT solver. We took a clique solver and made a SAT solver out of it, despite over its own objections. The poor thing doesn't know it's solving SAT. It just knows how to solve clique, and it thinks it's solving clique for us. But we disguise a SAT instance as a clique instance. It's like when you feed a child. You want to feed a child medicine. You wrap it in some candy, the pill, the medical pill, and the child's thinking he's eating some yummy candy. He's eating some bitter medicine, but he doesn't know it. That's what we're doing here. Okay, independent sets. What's an independent set? An independent set is a bunch of nodes that are not connected to one another. None of them are connected to one another. It's like a sort of a set of friends all connected. It's a set of enemies, non-mutual enemies, and none of which are connected to one another. That's what an independent set is. So I give you a graph in a parameter k, and I ask you, is there a independent set of size k? So it's almost like an anti-clique, right? How many get that? Independent set is an anti-clique. None of them are connected to one another. Because it's an anti-clique, it's actually easy to solve this problem. If you had a clique solver, you can solve the independent set. So here's a graph, and we're going to negate the graph. We're going to find a complement of this graph. So if there's an edge between these two nodes, there won't be an edge between these two nodes in the complement of the graph. If there is no edge here between these two nodes, we'll put an edge there on purpose. So we flip all the edges into non-edges and all the non-edges into edges. That's the complement of a graph. So if there is an independent set here, there's a clique there and vice versa. So here, there's an independent set, this node and that node and that node and that node. None of these four nodes are highlighted here, are connected to one another. There's no edge here, there's no edge there, there's no edge there, there's no edge here. That's an anti-clique. That's an independent set. Well, that means those four nodes must have been a clique over here, right? Because independent set here translates into a clique here. This is a clique of size 4. All these four are connected to one another here. There's the clique in purple. How many begin to see what's going on here? Yeah. So if we had an algorithm that finds us independent sets, we can immediately exploit an algorithm that finds us cliques. How? By negating the graph, inverting the edges and non-edges, which makes independent set NP-complete. So we just knocked down one more problem in Richard Karp's long list of 24 NP-complete problems in his 1972 paper. This one was easy. This transformation was not hard. It was easy to see that you could just flip and get the answer for the other problem. Any questions about that? How many see exactly what's going on here? Yeah. Any questions about this? And what's a transformation? Just negate the edges and non-edges. How fast is this transformation? How fast does it run to convert this instance of independent set, or excuse me, this instance of clique to this other instance of independent set? How fast is this F that transforms one to the other? Not hard, but silence is not an answer. What's the answer? Linear time, yeah, obviously. It's a pretty easy transformation. And even if it was quadratic time, it'd still be okay, because all F has to be is polynomial time. It doesn't have to be any particular polynomial, just as long as it's not exponential. So basically here, we took a independent set solver and converted it into a clique solver. And we already know that everything in NP reduces to clique through this other series of transformations we saw up to now. And now clique reduces the independent set, so independent set is also NP-complete. Now you see how it goes. It gets easier and easier to show more and more problems are NP-complete. And you don't have to do it from scratch. You just have to find a problem that's kind of mildly related to it, where the conversion is relatively straightforward, or maybe not so straightforward, but at least it works. And you get another NP-complete problem that you can stamp with your stamp of NP-complete. Now your group keeps growing and growing. And today we have tens of thousands of problems, all of which are NP-complete. And there's an infinite number more. And these 10,000 problems are not some esoteric, weird, unpractical problems. They're things we try to do every day, every hour of every day of our lives. Like find paths through connecting things and scheduling things and packing our boxes when we move and delivering packages by FedEx or UPS. These are all NP-complete problems. Almost everything we need to do daily turns out is NP-complete. It's such a ubiquitous phenomena, right? It's amazing that this is the case. So we converted a graph clique solver into an independent set solver there. So it's all about transformations, right? It's transforming problems to other problems. Very powerful phenomena. And in fact, you do that all the time when you program. How many know what I'm talking about? You're trying to accomplish some goal. You're going to solve some problem when you program. But you don't want to write from scratch all the code you need every time you program something. What do? You call subroutines from a library. like the sorting subroutine or subroutine that finds you minimum spanning trees or convex hulls or whatever else. You're calling a subroutine. So when you program, you do exactly that also. You transform a problem to another problem. So you're already doing this when you program, transforming problems to other problems by calling subroutines that solve other problems in order to solve problems that are not that problem. By wrapping a little bit of glue code around that subroutine, and the other problems are all of a sudden solved. By calling that subroutine for this seemingly unrelated problem, you're solving yet another problem that's not even related to the first. That's a transformation. Every time you write a program, you're invoking and creating transformations of problems to other problems. If you think about it abstractly enough, it's exactly what you've been doing all along as programmers. Think about that. Okay. Now we're going to see a transformation that's not so easy. So you can see a complicated one. So we're going to reduce satisfiability to graph colorability. So given a satisfiability instance, we're going to reduce it to graph colorability. So how do we do it? Take a 3-sat instance. So for every clause of the instance of 3-sat, every clause has exactly 3 variables or negations of variables. That's why we call it 3-sat, because each clause is of size 3. We're going to convert it into a piece of this larger graph of larger colorability instance. So for example, this clause here that says x plus y plus z, where they're all Boolean variables, is going to be converted to this piece of graph. And that's only a small piece of a much larger graph. I'm going to show it to you piecemeal, one portion of graph at a time, so it doesn't get too complicated all at once. I'm going to have 3 nodes here that correspond to the x and the y and the z. Graphs in nodes, these nodes are not labeled per se. I'm showing you that these 3 nodes represent the x and the y and the z. They're not necessarily labeled x, y, and z. A graph is just a bunch of nodes and edges. You can label it with whatever you want, and it's still the same graph. But this whole contraption here will act as a big OR gate. And this, we call it a gadget, because this is the historical name of what these kind of pieces of graphs or sub-transformations are called, gadgets. So this gadget here, that we convert this clause of the 3-sat instance into this subgraph, this gadget here is 3-colorable. This little piece of graph is 3-colorable if and only if this x plus y plus z is true in the satisfiability side of the house here. And you can think about this as a big OR gate, okay, where if x and the y and the z are both, any one of the x or the y and the z is true, then this output node t will be true also. And what is mean by true? Because nodes are not true or false. They're just nodes connected to other nodes or not connected to other nodes. I'm going to pick 3 colors to represent true and false and some third color that's not the true and the false, but some third color. So I'm going to also have a triangle of nodes here, the x and the x naught, and both of them are connected to each other, and both of them are connected to this third node that is a separate node. For every x and y and z and w, I'm going to have a triangle like that, x and x naught. Because in the colorability, x and x naught, because they're connected, they can't have the same color. On the satisfiability side of the house, x and x naught cannot have the same truth value, because if they did, it would be a logical contradiction. X and x naught cannot be equal to each other. They cannot both be true, and they cannot both be false, x and x naught. X and x naught, one of them is true and the other is false, or vice versa. They cannot both be true, they cannot both be false. Which nicely maps to this color constraint that both x and x naught, in terms of nodes, can't be assigned the same color in the colorability instance, because graph colorability insists that adjacent nodes have different colors, not the same color. And both of these nodes are connected to this third guy, which means both of these nodes are connected to a third color. So whatever that third color ends up being in the colorability instance solution, x and x naught cannot both be the same color as each other and the same color as this. So the other 2 colors besides this will be the truth and the false color, the colors that correspond to true and false. Colors cannot be true and false, they must be colors. But they correspond to true and false in a way that we'll see more clearly soon. Right? So it could be if this is green in some colorability solution, 3 colorability solution, this could be blue and this could be red, or this could be red, this could be blue, but they cannot both be red and they cannot both be blue, and neither one of them could be green. Okay. You'll see in a minute how it all fits together, because there's more coming up. This is not the end of it, obviously. So each clause in the formula will end up being this big OR gate, and whatever coloring we assign to this final graph, we'll be able to determine the satisfying assignment of the variables in the satisfiability instance that gave rise to this graph according to this transformation. So this is one big transformation we're watching unfolding before our eyes. Okay. And so here's what it looks like for a larger example, just so you see how that stuff on the previous slide gets instantiated. So here are the OR gate gadgets. Here's that triangle, and here are all the triangles for every variable x and x naught, y and y naught, and so on. Let's see how this Boolean formula gets transformed into a colorability, a 3 colorability instance, in a way that 3 colorability instance is 3 colorable if and only if that Boolean formula is satisfiable. That's a tall order, but here's how you can do it. So here's the OR gadget for the first clause. So it's red, color-coded, red here and red here. This is isomorphic to that. I just kind of skewed it a little bit. You'll see why in a second. How many see that this and that are the same graph? Yeah, okay, good. The second clause, so we just took care of the first clause. The second clause in green, similarly, will have this OR gadget here. But notice that the z already exists, so we just have to connect the z here, and we don't have to create another z. Every x and y and z appears only once in this graph, and the edges can connect it using long wires. It doesn't have to physically be right there. Nice thing about graphs, they denote topological relationships, not geometric relationships. So a graph, you can move the nodes all the way around, and it'll still be the same graph as long as the connectivity is the same, obviously. That's why we use graphics, in fact, to distill a topological set of relationships from the geometric underlying constraints. Right? So this blue node is the same blue node for all the gadgets. How many see that this gadget here is exactly the same as this gadget there, just with the wires a little bit twisted, that's all. So that's the second clause coming in here. The third clause is the blue clause, x naught plus y plus z naught, and that's this gadget here, that's the OR gate there, and that's that clause. So we're building the graph, building the colorability instance, the 3 colorability instance in particular, because we're not just showing colorabilities NP-complete, we're showing 3 colorabilities NP-complete, specifically. And if 3 colorabilities NP-complete, we can just use exactly 3 colors. If you take 3 and make it arbitrary, obviously that's at least as hard as just 3 fixed. How many understand that? So we're showing 3 colorabilities NP-complete much more powerfully than just showing colorabilities NP-complete in general, because the former implies the latter. Okay, and this triangle here is right there. So this triangle that we have to insert into the graph, there it is. This node here has to be connected to the other 2 nodes. And these 2 purple lines, actually these 3 purple lines, this purple triangle is this long purple triangle. How many see that it's the same? Yeah, topologically it doesn't matter, because it's just a triangle. It doesn't matter where they sit geometrically in the plane. So there's that triangle there. Now for every variable in its negation, we've got to create this effect here. So x and x naught will be connected to here. Z and z naught will be connected to each other, and both will be connected to the green, just like it should for all x's and y's and z's. For every variable, the variable is going to be connected to its negation. So x will be connected to x naught, and both will be connected to the green. So there's that triangle here for x. There's that triangle here for y. How many see that going on? So we're doing all of that. And at the end, we get this one big giant graph. Now, if we just so happen to be able to 3-color this big graph, the 3 coloring of this graph will immediately give us a satisfying assignment for this Boolean formula. How? Whatever color the x receives, if we were to 3-color this graph, we know that the x and the y can't be the same color as each other because they're connected. We know that the x and the y can't be the same color as this green, because all the x's and all the y's are all connected to this green via these triangles that we all inserted deliberately into this graph. So the only other 2 colors remaining is blue and red. So all the x's and the y's will be blues and reds, each one of them. How many can see that? Because they're all connected to the green, and they can't be green, because no 2 adjacent nodes can have the same color. So the blues and the reds will act as truth and false indicators. And by the way, there's nothing magic about green and red and blue. I could have used purple and pink and brown, or color A, color B, or color C. I didn't even have to call them by proper color names. How many understand that? It's just abstractions. You have to have three of them, and you can't use the same one for nodes that are adjacent. That's all. So when we say colors, don't think about it as colors, just three properties that have this kind of relationships. But without also generality, it's called green, red, and blue for the primary colors, because it looks nice and it's simple. So let's say there's a three colorability solution in this graph. And let's say this is the solution. This is a three colorability of this graph. Why? Because I only use three colors, blue and red and green. There's no fourth color here if you look at all the nodes. And if you look carefully, no two nodes that share an edge have the same color. Right? So if this is green, that's not green. And if this is blue, that's not blue, and that's not blue either. Once you paint this graph with three colors, you can read off the satisfying assignment for this Boolean formula from which this graph came. And in this case, the three satisfiability solution to this formula, read off of this graph, is X is true, Y is false, and Z is false. Right? Because this graph captures all these relationships that this formula asserts. These logical relationships that are asserted by the clauses and the variables and the negations of the variable in this formula are all captured by this graph according to colorability constraints. That's how we constructed this graph. That's why we constructed this graph in this way. So we convert a bunch of logical relationships up here into a bunch of colorability constraints down there. And so we converted a SAT instance into a graph in such a way that if we had a good, efficient graph colorability solver, three colorability solver, we can exploit it in this way to solve arbitrary satisfiability instances. That's an amazing feat, because graphs seem to have nothing to do with Boolean formulas. Boolean formulas are a bunch of Boolean variables that can be true and false. There's clauses, ands, and ors. Graphs have none of that. They should have nodes and edges. And colorability is assignments of colors. It has nothing to do with truths and falses and ands and nots and nors. But the two problems are intimately related in this transformation. They're tied together. So if we had a good colorability solver, this is how we exploit it into forcing it to solve SAT instances for us over its objections and despite its intentions to the contrary. Not that subroutines have intentions and objections, but it's exploiting one subroutine to solve a completely different problem that it wasn't designed or intended to solve. Okay. Just like we converted sorting into convex hull, that we have a convex hull solver, we can sort using it, so we can exploit a convex hull solver into sorting for us. I don't even remember that. Again, we talked about it over and over again. So here we're exploiting a colorability solver into solving SAT instances for us. And this transformation wasn't easy, it wasn't trivial, it wasn't obvious. And it took years to come up with it. Imagine somebody sitting down trying all sorts of little gadgets and seeing how they interrelate and what this colorability should look like, instance should look like based on this, so that to preserve this relationship, that this is satisfiable if and only if this is three colorable. And this doesn't give us necessarily the assignment, it just tells us that if you have a yes-no decider for coloring, immediately you have a yes-no decider for satisfiability instances. How many understand that? And what if you wanted the answer for the satisfiability or the colorability, and all you have is a yes-no decider? What do you have to do more or next? So if you have a decider, but you want it to actually give you the answer, not just tell you that one exists, what can you do to force that to happen? An easy question at this point. What do you do? to convert a decider into an optimizer in general, for any problem, not just colorability, not just satisfiability. Say something. Play 21 questions with it. How many get that? So even if you have a subroutine that doesn't give you the colorability, the colorization of the graph, just tells you that one exists. You can force it to give you the colorization by playing 21 questions with it. I'll leave exactly up to you exactly how that would work for colorability. We already know how it works for satisfiability. Say P and X or P and not X, and extract one variable at a time from it. You can do the same thing for colorability. Slightly different, but exactly the same principle. Okay, and and next time we'll talk about what makes colorability difficult exactly, and why is it so hard to colorize graphs? Is it the degree of the nodes? Is it whether the graph is planar or not, or is it the fact that you only using 3 colors and not more colors? And the answers will be no, 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 and no. There's something very inherently difficult about colorizing graphs using only 3 colors, even if the degree is bounded to be no more than 4, even if the graph is supposed to be a planar graph, which is a very special kind of class of graphs, it's still NP-complete, despite all of these constraints and restrictions and specializations of the problem. There's something very inherently difficult about colorizing graphs. Just like SAT, satisfiability wasn't about the size of the clauses. Because even if the size of the clauses was only 3, that's still NP-complete. So it's not because the formulas have this big complicated format, structure. It's because there's something inherently difficult about figuring out exactly what combination of values to assign to variables or colors to assign to nodes to find some overall good answer. And so we'll go through all of that too next time. For now, any questions about this? So now we're deep into graph coloring, and we'll go even deeper into graph coloring just so you see how it goes. And question was, yeah. Why do we need a false node? Oh, because you want this node here to be different than that node here and different than that node here, because all the variables are connected to this green node, which means they all have to be one of the other 2 colors, true and false. And keep in mind that these colors are not necessarily inherently true and inherently false. They represent truth and false. So by making all the nodes, all the x's and the y's and the z's connected to this, they're forced all of them to be either that or that, but they can't be both. The x and the y, the x and the x naught cannot be both true or cannot be both false. I'll take some more questions after class, but let's stop here. Next time we go even deeper into colorability and NP-completeness, and then we'll talk about approximation algorithms, which are even cooler than that. So see you next time.